Very good evening, students.
Good evening,
Good
sir.
evening, sir.
Good evening, all. So last class we have been discussing about radius ratios and different types of crystals. Like in that we have seen that if the triangular void has to be formed, coordination number would be 3. Obviously triangular void means, and limiting ratios, limiting radius ratio, radius of cation by radius of anion is 0.155. Below that radius, the triangular void or crystal is not formed. Range is 0.155 to 225. In that range, we can have triangular void. Similarly, we can have tetrahedral void, octahedral void, cubic void. Every calculation we have seen, and these are the respective radius ratio values. And for values less than 0.155, the crystal is not going to be existing. Right? After this, as I have told you, we'll be studying about different crystalline structures. The first one is rock salt structure. Best example of rock salt structure you can take is NaCl. NaCl, sodium chloride. We have Na plus and Cl minus ions. Generally, which will form the lattice? Generally, anions. The large size anions, they will be forming the lattice, and the small size cations, they will occupy the void spaces. Which void spaces are going to be occupied? How do we know that? Which void space, like we can have tetrahedral void, octahedral void, which void is going to be occupied, that will be decided based on radius ratios. So first rock salt structure, we have to form a lattice out of chloride ion. Generally Cl minus, bigger Cl minus form cubic close packing, and a small Na plus occupy the octahedral voids. How do you know octahedral voids are going to be occupied? By the radius ratios. Simple logic. You form the lattice CCP, cubic close packing. In CCP, what is the unit cell? We have seen the close packing of 1 dimension, 2 dimension, 3 dimension in the last class. In cubic close packing, what was the unit cell present? Face centered cubic. Yes or no? Face centered cubic. In FCC, where are the tetrahedral void, students? In FCC,
At diagonal points.
on the body diagonal, every body diagonal will be having 2 tetrahedral voids, and the tetrahedral voids will be dividing the body diagonal in the ratio of 1:2:1. Very good. And where are the octahedral voids? Octahedral voids will be at
Center.
very good, body center as well as edge centers. So now based on radius ratio, we find that the cation should be occupying the octahedral voids. So that was the idea. Okay. So that is your respective NaCl crystal. Chloride ions are forming the CCP, cubic close packing means FCC crystal, FCC unit cell. Na plus will be present at the octahedral voids. Okay. CCP means FCC unit cell. CCP has FCC unit cell. The explorer diagram of CCP we have seen, and from that you found that FCC unit cell is present. CCP has FCC unit cell. Na plus are present at octahedral voids. Octahedral voids are actually present at edge center and body center. Edge center and body center. Right? This will be the structure. You can just look at the structure of NaCl, where you have chloride ions a lot at all the corners as well as the face centers because FCC lattice, and Na plus ions are present at the octahedral voids. So at every edge center you have Na plus, as well as at the body center also you have Na plus. Animation clear or not?
Yes, sir.
Yes, right. Very good. Each Na plus is surrounded by 6 chloride ions. Look at the structure now. Look at every Na plus. Each Na plus is surrounded by 6 chloride ions, and each chloride is surrounded by 6 Na plus. Look at any chloride, like I am talking about this chloride. Here we have chloride. It is surrounded by this Na plus, this one Na plus, and this one Na plus. Exactly opposite to this, you will have one more Na plus here. Exactly opposite to this, you have one more here. Exactly opposite to this, one more here. So every chloride ion will be surrounded by 6 Na plus ions, and every Na plus ion is surrounded by 6 chloride ions. So 6:6 type. Coordination number of cation and coordination number of anion, 6:6. So number of Na plus and Cl minus in each unit cells. Where are Na plus present? Number of atoms in unit cell, or number of particles, we can say number of particles in unit cell. Particles in unit cell will be is equals to number of octahedral voids. Can I say?
Yes.
Yes or no? Number of particles in the unit cell is equals to exactly equal to number of octahedral voids, but the number of particles in the unit cell is, and if you try to compare the tetrahedral voids is equals to twice the number of particles in unit cell. So number of particles, which particle is actually forming the rod is chloride. So how many chlorides are there?
4.
So 8 chlorides, 8 corners, 8 into 1 by 8, 6 chlorides at 6 centers, 6 into 1 by 2. That is nothing but 4 Cl minus ions are there. And obviously 4 Na plus. Where are the Na plus present? 12 edges are there. 1 by 4 is and 1 into 1. So 4 Na plus, 4 Cl minus. So number of Na plus and Cl minus in the unit cell is 4. Number of Na plus ions 4, number of Cl minus 4 in a particular unit cell. So can I say number of NaCl per unit cell is 4? Number of unit cell, number of NaCls also. Na plus is 4 are there. Cl minus are also 4. So number of Na plus and Cl minus combinedly, number of NaCl will be 4. The density of NaCl crystal, density of NaCl is equals to mass of NaCl, density is equals to mass by volume. Mass of NaCl, density of NaCl crystal is equals to density of NaCl, like unit cell, whatever the present. Mass of unit cell divided by volume of unit cell. So unit cell will be having a volume of A cube. What is the mass of unit cell? Number of NaCl 4 into molar mass of NaCl, divided by Avogadro number, because mass of NaCl is nothing but like 1 mole of NaCl will be having a weight of molar mass. Molar mass is nothing but weight possessed by 1 mole of NaCl. So molar mass divided by Avogadro number is nothing but mass of 1 NaCl. The edge length of the unit cell is given by 2 into radius of cation plus radius of anion is equals to, that is edge length. So A by 2 is equals to radius of cation plus radius of anion. How to find out? You can easily understand. Here at the corner we have chloride ion. At the edge center we have Na plus. At the other corner we have again chloride ion. So this is radius of anion. This is also radius of anion. Radius of anion. This is nothing but 2 times that of radius of cation. So I can say 2 times that of radius of anion plus 2 times that of radius of cation is equals to edge length A. 2 times that of radius of cation plus radius of anion is edge length A. So from this you can actually find out, like radius of cation will be given in some cases, radius of anion will be given in some cases, and in that case you can actually figure out the edge length A. Okay, so for NaCl, for rock salt structure, you can say 2 times that of radius of cation plus radius of anion is equals to A. Is that clear? Is everything clear so far?
Yes, sir.
Yes. Next type of structure we'll study then. Zinc equivalent structure ZNS. ZNS will have Zn plus 2 and S minus 2 ions. ZNS will have Zn plus 2 and S minus 2 ions. Which are larger ions generally? S minus 2 anions. Anions will form the CCP again. S minus 2 are forming CCP means where are they present? Corners
And
Face centers.
and face centers. And if you try to look at the radius ratio, where are Zn plus 2, like we don't know. Like we know S minus 2 is forming the cubic close packing based on its size. But now we have to fill up the Zn plus 2 ions. Where are Zn plus 2 ions filled? That we don't know. They can be filled in octahedral or tetrahedral. To know that where they are going to be filled, we find the radius ratio. Upon finding the radius of cation by radius of anion, since it is belonging to 0.225 to 0.414, you can decide that the Zn plus 2 are filled in octahedral voids or tetrahedral voids?
Tetrahedral.
Tetrahedral voids. Okay, they are all present in the Zn plus 2 are occupying all the tetrahedral voids. Now number of tetrahedral voids will be how much?
Twice that of.
Number of tetrahedral voids is equals to twice that of number of particles. So that will be 2 into 4. That will be 8. Yes or no?
Yes.
So can I say all the tetrahedral voids are occupied? Number of tetrahedral voids are 8. If every tetrahedral void is occupied, 8 tetrahedral voids, 8 into plus 2 will form plus 16. But S minus 2 is forming only corners and face centers. So S minus 2 will be occupying only at the corners and face centers, means only 4 number of S minus 2 are present. So minus 8 will be the net negative charge. But if all the tetrahedral voids are occupied, then you will have plus 16. But whenever charge is not neutralized, obviously that crystal is not going to be stable. So we can say that Zn plus 2 is occupying the tetrahedral voids, but only alternate tetrahedral voids, not all tetrahedral voids. Is that clear or not?
Yes, sir.
So larger S minus 2 forms ECP arrangement and smaller Zn plus 2 fill half of the alternate number of tetrahedral voids. You cannot have, like, tetrahedral voids are present in the small cubes of a larger cube. If I try to divide the larger cube into 8 small cubes, every small cube will have tetrahedral voids. At the center of tetrahedral void, if you keep like one atom here, other atom here, one atom exactly same, like we have this type of crystal, right? If I give one tetrahedral void here, other here, one more here and one more here, then only this part of the unit cell is going to get all the positive charge. That will not be, again, like charge is not distributed uniformly. Like uniformity is not going to be maintained. So if we have one positive charge here, other will be here. If you have one positive charge here, other will be here. So alternate tetrahedral voids are going to be filled in such a way such that you will have uniformity in the charge as well as stability. That is how the unit cell looks like. So you can just look at the animation, how the Zn plus 2 are actually present. S minus 2 forming the lattice, Zn plus 2 occupying the alternate tetrahedral voids, such that the charge is going to be greatly normalized. And here also you try to figure out the respective relationship between radius of cation and radius of anion. Can I say, like, this particular tetrahedral void is filled? Here you have a respective anion. It is nothing but, this distance is nothing but 1/4 of the length of body diagonal or not?
Sir.
Yes or no? Because the tetrahedral voids divide the total body length into 1:2:1 ratio. So if I look at this particular distance, that is from the corner to the center of tetrahedral void, you will be having 1/4 of the length of body diagonal. So radius of cation plus radius of anion, these two are touching. Radius of anion plus radius of cation, that should be equals to 1/4 times that of length of body diagonal. So what I can write, radius of cation, what is the cation? Zn plus 2. Radius of anion, S minus 2, is equals to 1/4 times of length of body diagonal. What is the length of body diagonal? √3. Radius of Zn plus 2 plus radius of S minus 2 is 1/4 times that of √3. And how many Zn plus 2 are there in total? 4 Zn plus 2, because 4 are present at alternate tetrahedral voids. How many S minus 2 are there? 4 are there. So what is the coordination number type? 4:4 type. 4:4 type. Coordination number of both Zn plus 2 and S minus 2 is 4. And also we have 4 Zn plus 2 and 4 S minus 2 per unit cell. Coordination number means if you try to look at the respective S minus 2, around each S minus 2 you will have 4 Zn plus 2. And around each Zn plus 2 you will have 4 S minus 2. So coordination number will be 4:4 type, and they will form number of formula units. Number of formula units is 4. Number of formula units is 4. Okay. Coordination number of both Zn plus 2 and S minus 2 is 4:4 type. Formula units of Zn plus per unit cell is 4. Density of Zns is 4 into molar mass of Zns, because Z is 4. 4 formula units are there. 4 into molar mass of Zns divided by Avogadro number into a cube. And radius of Zn plus 2 plus radius of S minus 2, that is found to be √3a/4. Is that clear, students?
Yes, sir.
Yes. Cesium chloride structure, you try to figure out. Cesium chloride structure, which will be forming the lattice. Cl minus forms lattice. Yes or no?
Yes,
Cl
sir.
minus will form the lattice, and where is respective cesium plus present? Cs plus is present at body center. Body center. Understand this point? You may again ask a question, sir, how we can say Cl minus is forming the lattice? Generally, lattices and form the lattice. Cl minus, the anions are generally forming the lattice. Cl minus are forming the lattice, but not CCP lattice. What type of lattice is going to be formed? The the Cl minus are going to present only at the corners of the cube. The Cl minus are present only at the corners of the cube, whereas Cs plus is present at the body center. Understand this point carefully. If the particles which are forming the lattice, if they are present at corners as well as at the body center, then it is body centered cubic lattice. But here the lattice is formed by chloride ions, where the chloride ions are present only at the corners. So simple cubic type. And also the cesium plus, that is actually present at the body center. This is the structure. And around each chloride ion, how many cesium plus ions are there?
1.
You have to consider all the unit cells. You are just considering this unit cell, Faizan. Okay.
8.
Here
8.
8 are there, no? Because every corner, with respect to that corner, you have this. Here we have cesium plus. Like in the bottom, four corners will be there, like 4 body centers. And above layer also we have 4. So around each Cl minus you have 8 cesium plus. Around each cesium plus you have how many chlorides? 8. Because cesium plus is again at the body center. So all the corners. So what is the coordination type?
8
8 is to
8 is to 8 coordination type. And how many, like per unit cell, number of formula units?
1.
8 from
Number of formula units. Like we have 8 chloride ions at 8 corners, so 8 into 1 by 8, that is 1. And 1 cesium plus at the body center, so 1 into 1. So number of formula units, number of cesium plus is 1. Number of chlorides is also 1. So 1. What is the radius, like radius of cation plus radius of anion relation? Can I say this is exactly half of the length of body diagonal or not? If I try to compare like the distance between radius of cation and radius of anion, radius of cation plus radius of anion is half of
length of
length
body.
of body diagonal. That means radius of Cl minus plus radius of Cs plus, that is equals to half of root 3a. Okay, this was a complete information. Cl minus are at the corners of cube and Cs plus at the body center cubical void. Cl minus corner, Cs plus body center. And this was the information. Coordination number of both cation and anion is 8. So 8 is to 8 coordination type. Formula units of CSCl per unit cell is 1. So Z is 1. So 1 into molar mass of CSCl divided by Avogadro number into A cube. Radius of cation plus radius of anion is half of root 3a. Half of root 3a. Is everything clear so far?
Yes, sir.
Yes, sir.
That's right. Now next type of crystal. Fluoride structure. Fluoride means you have Ca plus 2 and F minus. You can look at now, until now, whatever structures we have seen, NaCl, ZnS, CSCl, the cation and anion has same charge. But in fluoride CaF2, cation has plus 2, whereas anion is minus 1. So for every cation, we require 2 anions so that charge neutrality will be maintained. So now here in fluoride structure, what happens is the respective cations will form the lattice. Okay. Here Ca plus 2 will form CCP. CCP means what type of unit cell? FCC unit cell.
Safe and
Yes or no? FCC unit cell is present. So Ca plus 2 are present at corners as well as face center. Ca plus 2, how many are there? 4 are there.
4.
So F minus, where should be present? Based on radius
At
ratio,
octahedral
it was,
voids.
yes. Based on radius ratio, it was found that they are present at tetrahedral voids. But how many tetrahedral voids? All the tetrahedral voids are only half. All tetrahedral voids, because all the tetrahedral voids occupied by F minus means 8 into minus 1, that becomes minus 8. If you can say 4 Ca plus 2 are there, they will produce a charge of plus side. All tetrahedral voids occupied by F minus, they will have a charge of minus H. Okay. F minus occupy all tetrahedral voids and total positive charge is equals to plus 8 and total negative charge is equals to minus 8. And what type of coordination number? You try to think of coordination number like around CA plus 2 you talk first. This is CA plus 2. Around each CA plus 2, how many F minus are there? Nearest neighbors. Coordination number of cation Ca plus 2 is present here. Here we have 1. Like can I say here also we'll have 1 in the other unit cell?
8.
Here also we'll have 1. Like I am talking about this particular. If you try to think of, you can think of one corner like this. Like this top corner you think. Like here one room is there, next other room, back side also one more room, diagonally also one more room. From there corner to this particular corner you have a diagonal, bar diagonal. From there to this 1/4 of the bar diagonal you have one tetrahedral voids. Here you have one F minus. Similarly, exactly the other room also we have F minus. The back side room also one F minus. The diagonal room also one F minus. These are all the rooms in this particular floor. The same corner is shared with the above floor also. So above also we have 4 more F minus. So what is the coordination number of Ca plus 2?
8.
8. But now look at the coordination number of F minus. This F minus is going to be surrounded by how many nearest neighbors? One is this one?
4.
Yes or no? Yes, it will be surrounded by 4 nearest neighbor. One is this one is this one, and one is this one. Yes, 4 nearest neighbors are there. Like what is the coordination type now? Cation is to anion.
8
is to 4. 8 is to 4 coordination type. Coordination type is every cation is surrounded by 8 F minus. Every anion is surrounded by 4 Ca plus 2. Coordination number of cation is 8. Coordination number of anion is 4. 8 is to 4 type. Number of formula units. How many Ca plus 2 are there? 4 are there. How many F minus are there? 8 are there. So number of formula in each CaF2 molecule, CaF2, we have 1 Ca plus 2 and 2 F minus. Therefore, 4 Ca plus 2 and 8 F minus will be equivalent to 4 CF2 formula units. So in the particular unit cell, we have 4 CF2 molecules, right? And this is a distance, like radius of cation, like whenever we have tetrahedral void occupied, radius of cation, radius of Ca plus 2, plus radius of anion, radius of F minus, that is nothing but 1/4 of length of bar diagonal, that is 1/4 of root 3A. Yes, Sonia, the name is assigned based on the anion like fluoride type. We also have anti-fluoride type. Like the next molecule is Na2O, where we have anti-fluoride structure. There you have fluoride F minus occupying the Na2O, right? O2 minus anion is occupying the lattice, and cations are actually present at the tetrahedral voids. Okay. This is fluoride structure. CaF2 is fluoride structure. In CaF2 only we have cations forming the lattice. In CaCl, in NaCl, and in ZnS and Na2O, in all these we have anions occupying the lattice. In CaF2, cations will occupy the lattice. Okay. As I was saying, next structure, anti-fluoride structure. First try to figure out which will form the lattice. As I have told you, Na2O, which will form the lattice?
Na. Oxygen.
Na2O or oxygen, O2 minus. As I have told you, CaCl, NaCl, ZnS, Na2O, anion form the lattice. CaF2, cation form the lattice. Okay, so O2 minus is present at which positions? Everywhere, like only in CaCl you have simple cubic where cations, where anions are actually presented only corners, but remaining all we have CCP arrangements. O2 minus they are presented like a cubic close
Percentages.
packing. Yeah, cubic close packing means
Corners.
FCC unit cell. So how many O2 minus are there? 4 O2 minus per unit cell. Per unit cell. Therefore, total negative charge, because they are
-8.
presented, yes, they are presented corners as well as space centers. So 4 O2 minus per unit cell. So 4 into -2, that is -8. So -8 means obviously based on radius ratio, we found that Na plus should be presented tetrahedral voids, and all the tetrahedral voids should be occupied because 8 tetrahedral voids is there. Total tetrahedral voids is equals to 8, and all these are occupied by total tetrahedral voids is equals to 8, and all these are occupied by what do you say? Na plus ions. Na plus ions. Coordination number of O2 minus, you try to figure out. O2 minus is surrounded by how many Na plus? O2 minus is
8.
actually, it is surrounded by 8 Na plus, and coordination number of Na plus, each Na plus is
4.
surrounded by 4 O2 minus. So for coordination number type, coordination type, first cation you have to write, then anion. 4:8 type. 4:8 type. And how many Na2O present per unit cell? How many formula?
4.
Okay, formula units is 4. 4 NaCl, 4 Na2O formula units are there. Density again there you will get 4 into molar mass of Na2O divided by Avogadro number into A cube. And radius calculations, right? Radius ratios, sum of radius ratios, radius of cation plus radius of anion. Again tetrahedral what's occupied? No. So 1/4 of length of word angle, that is √3a. So radius of Na plus radius of O2 minus is equals to 1/4 times that of √3a. So based on this formula, you have to calculate the respective, like whatever some quantities will be given to you, other are not given. So based on that, you have to find out. Okay. O2 minus forms CCP lattice and Na plus are filled in all the tetrahedral voids. Density of Na2 is equals to, like a coordination number type is, cation is 4, anion is 8, so 4:8 type. Number of formula units of Na2O is 4. Density of Na2O is 4 into molar mass of Na2O divided by Avogadro number into A cube. Yes or no? And you write 4:2 type only, you don't do the calculation and say 1:2 type. Okay, you have to understand this coordination type gives the direct idea to give the understanding, like every cation is surrounded by how many anions, and every anion is surrounded by how many cations. Radius of cation plus radius of anion is 1/4 times that of length of bidiagonal, that is √3a. Is everything clear, students? Yes or no?
Yes, sir.
Yes, right. Very good. So then we have the structure of diamond. In the diamond, what happens? Do we have cations and anions? Is it a ionic solid?
No, sir.
Until now, whatever we have studied, NaCl, CaCl, ZnS, CaF2, Na2O, all these are ionic solids. But how many types of solids are there?
No, sir.
We have crystalline solids. In the crystalline solids, we have metallic solids, covalent solids, ionic solids, molecular solids. We are just looking at a very tiny part, ionic solids, in that some categories. That is what they are in your 12th standard. Metallic solid structures also will be different. Molecular solid structure will also be different. Covalent solid structure will also be different. Let us look at one example of covalent solid, that is structure of diamond. In diamond, what happens? The carbon atoms form FCC unit cell, that is CCP, and alternate tetrahedral voids are also occupied by coordinate atoms. Generally, ionic solid, what we say, one anion generally form the lattice, means cations will be occupying the void spaces. But here in the covalent solid, we do not have cation, we do not have anions. The atoms are repeating 3D structure. So the carbon atoms are forming the FCC. So carbon atoms are present at corners and face centers. First, if you look at the lattice, and also alternate tetrahedral voids, and also alternate tetrahedral voids. Understood this point or not? The carbon atom form FCC and alternate tetrahedral voids were also occupied by corner atoms. Now we try to think of, like, same, imagine the case, radius of, here if you have anion, here if you have cation, what do we say? Radius of cation plus radius of anion is how much times that of length of void angle?
1/4.
1/4. 1/4 of length of void angle is √3a. But what is cation? Cation is also same carbon. So radius of carbon, anion is also same carbon, radius of carbon. So radius of carbon atom plus radius of carbon atom, that is nothing but 1/4 into √3a. What is R? R is nothing but radius of carbon atom. So what is the relationship now?
√3a by 8.
R is equals to √3a by 8. That is, radius of the carbon atom in the diamond structure is actually equal to 1/8 times that of 1/8 times that of length of body angle, that is √3a. And what is respect to we'll say Z value? Z value is how much? Z is
8.
equals to, they are present at corners first, so 8 into 1/8. They are present at face centers, 6 into 1/2. They are also present at alternate tetrahedral voids. Tetrahedral voids are how many? 8.
4.
Alternate means 4 into 1. That is 8. So Z is equals to 8. Very good. So what is your respective packing fraction? You calculate packing fraction. Packing fraction is equals to total volume occupied, that is Z into 4/3 pi r cube divided by a cube. What is Z? 8. So we can write down packing fraction is equals to 8 into 4/3 pi r cube. R and A relation we have given already here. 4/3 pi r cube divided by a cube. A is nothing but 8r by √3. So 8 into 8 into 8. A is equal to 8r by √3, right? So r cube divided by 3 √3. √3 into √3 becomes 3, 3 √3. 8 one times gets cancels out. 3 one times gets cancels out. You will have what? R cube gets cancels out. 4 pi divided by 4 √3 pi divided by 8 into 8, 64. That means pi by √3 pi by 16. 4 by 64 is 16. √3 pi by 16 is the packing fraction. You try to calculate this value, all of you. .34 Karthik says. So packing fraction of diamond is 0.34. So that means only 34% of the space has been occupied in the unit cell of diamond. In the respective unit cell of diamond, only 34% occupied. You may ask a question, sir. You said that greater the packing fraction, like whenever we have close occupying, there you will have more stability. There it should be having more melting point. Then why you are saying there are some crystals where 90% is also occupied? There are some crystals where 74% is the space occupied. Then why you are saying in this, like diamond is going to have the extremely high melting point? There you have cations and anions. Between cations and anions, the electrostatic force of attraction are present. But here the structure of diamond, although 34% is occupied, the structure of diamond will be in such a way such that it will be everywhere you have a bonds, covalent bonds. Because of those covalent bonds, the 3D structure will be having extremely high density, extremely high melting point. This is how the structure is present. Earlier we have not written like this. In any of the ionic crystals, have we directly written the bonds? No, we have just placed the respect to cations and anions. Here we have a bonding in such a way. There is a bonding in such a way such that the 3D structure, whatever it is going to produce, that will have the extremely a high melting point, it will be very hard. The carbon atoms form FCC and alternate tetrahedral voids are also occupied by carbon atoms. What else we can say? Z is equals to 8, coordination number is 4. Coordination number will be 4 obviously because every atom is surrounded by 4 other atoms. Root 3a by 4 is equals to 2r, that is equals to density of carbon like a distance, like between the cation and anion. If you try to imagine, that is nothing but radius of cation and radius of anion. But here cation and anion not there, both are carbon atoms. From there you can find out the packing fraction as 34%. Is that clear, students?
Yes, sir. Yes, sir.
Yes, right. So these are the different structures which you can think of. And on increasing temperature, coordination number decreases as average kinetic energy increases, as we can say molecular motion increases, as molecular motion
Yes,
increases.
sir.
And on increasing pressure, coordination number increases as particles are forced to move closer. Particles were forced to move closer. But the application of pressure will be very high. Like we have to apply very high pressure to actually move the respective crystal lattice side particle. Next type, we have defects or imperfections in solids. Although we have discussed a lot about solids, but no solid is pure. There is no pure solid, there is always some imperfection. There is always some imperfection in the solid. What types of imperfections we can have and how we can understand all these types, that we are going to study now. And what types of imperfections we can think of, students? Imperfections in solid.
Non-stoichiometric.
Non-stoichiometric defects as well as stoichiometric defects. Like crystal defects, if you try to think of, we have stoichiometric defects, impurity defects, and non-stoichiometric defects. We'll try to understand. The crystal in which all the lattice points are occupied by the component particles or groups of particles is called ideal or perfect crystal. Ideal crystals are possible at absolute zero. Absolute zero, is it possible to achieve?
No,
No,
sir.
sir.
Absolute zero is not possible to achieve. That means there is no ideal crystal in reality. Okay, there is no ideal crystal in reality. That means every crystal lattice point perfectly occupied means that is a perfect crystal, which is only possible at absolute zero. As the temperature increases, like above absolute zero, obviously high temperature is there. Due to increase in molecular motions, what happens? The ions may lose their usual sites and either miss their positions or occupy interstitial positions in the crystal. That means what they are going to have? They are deviated from the perfect arrangement. Those deviations are nothing but defects. Simple terminology, what you can say? Exactly at the specific lattice site positions, ions are not present. They will be deviating from their respective positions, and that is why those deviations are leading to respective defects or imperfections. Defects or imperfections in solids. If in a crystal complete lattice of ions along a line disappear, along a line if all the ions are been disappearing, such defects are said to be line defects. Along a line, if all the points are disappearing, then that is said to be line defects. Defects in crystals are produced either due to thermal effects or by addition of certain impurities known as doping. We can also add an impurity to have doping. Yes or no? We can add an impurity to do the doping, or in a crystal complete lattice of ions along a line disappear. Such defects are called line defects. And we have added the impurity in the metallurgy also. If you think of like electrolytic reduction, we have a particular metal. Whenever you're trying to decrease the melting point, what we will do, students? We'll be adding some other ionic crystals like NaCl. Along with NaCl, you add CaCl2. NaCl is a particular metallic structure, like a particular ionic compound, where if I have to produce Na plus ion by the electrolytic reduction, the Na plus will be moving the NaCl. If you try to write the electrolytic reduction, what happens? Na plus will form, the NaCl will form Na plus and Cl minus. cathode is negatively charged, anode is positively charged in electrolytic cell. So Na plus will be reaching the cathode, at cathode reduction occurs to form Na. But to do the electrolytic reduction of NaCl, what I have to do? I have to decrease the temperature of NaCl. To decrease the temperature of, to decrease the melting point of NaCl, what I have to do? I have to add some impurity like CaCl2. The impurity, whatever you are going to add, like I have told you, CaCl2, whenever you try to add to NaCl, the Ca plus 2 occupy some of the lattice sites of Na plus. Because of that, what happens? If I am doing the electrolytic reduction of NaCl, I can take molten NaCl, Na plus and Cl minus are going to produce. Na plus will be going and depositing at the cathode. But the temperature, the melting point of NaCl is high. To decrease the melting point, what I can do? I can add CaCl2. You may ask a question, how the CaCl2 addition will decrease the melting point? The CaCl2 will have Ca plus 2 at respect to, like NaCl. NaCl means, in NaCl, where the Na plus ions are there? Na plus are present at octahedral void, Cl minus are forming the lattice. Now, if I try to add CaCl2, the Ca plus 2 will occupy the octahedral void. To replace or to keep one Ca plus 2, how many Na plus has to be replaced?
2.
So, because of addition of CaCl2, so that Ca plus 2 ions can occupy, some of the Na plus ions are lost. So, we have some vacancies developed or not?
Yes.
Because of development of vacancies, what happened to the lattice energy? Increased or decreased?
Decreased.
Decrease.
No, imagine the case like every octahedral void is completely packed. Now we are removing the some of the ions. In the earlier case where every octahedral void and every corner and the phase center are occupied, there you have more lattice energy, more electrostatic force of attraction. Whenever some of the vacant positions are there, there you have less electrostatic force of attraction. Because of less electrostatic force of attraction, less is the lattice energy. So lattice energy of pure NaCl should be higher when compared to lattice energy of NaCl in the presence of some impurity like CaCl2. So because of that, melting point will be decreased or increased? Melting point will be decreased. Because of that, also can I say conductivity has been increased? CaCl2 addition. Because more number of ions are there, Ca plus 2 and 2 Cl minus, NaCl gives Na plus and Cl minus. So the addition of impurity in the particular metallic crystal in the electrolytic reduction, that is helping in decreasing the melting point, also in increasing the respective electrical conductivity, so that the electrolytic reduction can also be done, which is just an application of like metallurgy. Like that is how we need to understand. So doping means when to add an impurity, the impurities added will be occupying respect to crystal lattice sites. Because of the positioning of these ions at the crystal lattice sites, the lattice energy decreases. Because of decrease in lattice energy, the melting point decreases. Because of decrease in melting point, the easily the reduction can be done.
Sir?
Yes, please.
Sir, SRP of calcium is more than that of sodium, then why doesn't calcium deposit at cathode?
Because calcium is not the crystal lattice structure, like it is just added to the impurity. The majority is Na plus. Okay, they are just impurities, not added in the stoichiometric ratios. The added substances, whatever you are adding, they are not added in the stoichiometric ratios. Okay, that is the main reason.
Okay, sir.
Our metal is NaCl, no? So only some of the lattice sites they were occupied by Ca plus 2, just to reduce the melting point as well as to increase the electrolytic conductance. And this Ca plus 2, once it is occupying the respect to crystal lattice site, it will have electrostatic force of attraction with 2. The Ca plus 2 occupied means the 2 chlorides will also have electrostatic force of attraction. Right. Defects or imperfections in solids. So although we have said line defects, but line defects we don't study. We only restrict ourselves to point defects, that is stoichiometric defects, impurity defects, and non-stoichiometric defects. Stoichiometric defects are again Schottky defect and Frenkel defect. Impurity defects again one classification. Non-stoichiometric defects are metal excess defects and metal deficiency defects. So crystal defects, we can have point defects, we can have plane defects, we can have line defects. But we are studying only point defects. We are not studying line defects or plane defects. Line defect means along a particular line, all the ions can be disappearing. Along a particular plane, all the ions can disappear. That we are not studying. We restrict ourselves in the 12th standard to the point defects, like only some of the points are disturbed, not throughout the plane or throughout the line. These point defects were actually classified into stoichiometric, impurity, and non-stoichiometric. Stoichiometric means they are again classified as Schottky and Frenkel. Non-stoichiometric as metal excess and metal deficiency. What is Schottky defect? Can anyone say?
The absence of anion and cation at equal
Yes.
proportion.
First, we'll be having the stoichiometric defect. Stoichiometric defects means stoichiometry is maintained. First one. Schottky defects, these are type of defect which is produced when equal number of cations and anions are missing. When equal number of cations and anions are missing from their respective positions, leaving behind a pair of holes, the crystal as a whole remains neutral because the number of missing positive ions, that is cations, and negative ions, that is anions, are same. Number of cations and number of anions, whatever you are going to have, since they are same, so you are going to have electrical neutrality maintained. And this kind of defect is nothing but an example of vacancy defect or not? Yes or no?
Yes.
Yes or no? Like it is like a vacancy defect only. This is a point defect where equal number of cations and anions are missing. This is just a vacancy defect, right? And because of Schottky defect, what happened to the let us say density?
Decreases.
Density of the crystal should decrease because some of the ions have been removed. What happened to the conductivity? The crystal begins to conduct electricity or not?
No.
Conducts it.
Why? If it conducts, why? If it not conducts, why?
So because equal number of cations and anions are repeated, therefore neutrality.
Yeah, electrical neutrality is there, so it should be a conductor or non-conductor?
Non-conductor.
Non-conductor. But imagine the case, Faizan. So like here we have respect to, like this is a scenario. Here we have this position is occupied by respect to cation. And here we don't have any cation. This is nothing but hole. Let us say this cation present here can move toward this particular hole or not?
Yes, sir.
Under the application of electric or magnetic field, the ionic movement still occurs. Although they have electrostatic force of attraction, although we have equal number of cations and anions, because of the presence of holes, the ionic movement will still occur. So that will be acting as a conductor. Okay. The Schottky defect, because of Schottky defect, the crystal begins to conduct electricity because of ionic mechanism, where the ions can move towards the respective holes. And also, what happened to the lattice energy? Lattice energy should decrease or increase? I have removed some of the ions, no? The electrostatic force of attraction decreased, so lattice energy should decrease. The presence of voids will lower the lattice energy. It will decrease the density. It will also make the crystal to be a conductor. So these are the main points which you can understand. What happened to Frenkel defect? We'll discuss first Schottky, then we'll go to the Frenkel. Ideal crystal, from the ideal crystal, if some of the ions have been removed, so it will be forming respective void space are there, which is nothing but Schottky defect. Schottky defect, it is a kind of vacancy defect. Schottky defect appears generally in any compounds in which radius ratio is not far below unity. That means radius of cation should be close to radius of anion. In that condition only you have Schottky defect. For Schottky defect, coordination number of the ion should be high. Example of ionic solids showing this effect are NaCl, CaCl. All these are the respective example. You may ask a question, sir, why? Sir, why the radius of cation should be approximately equal to radius of cation, or cations and anions should not differ in size? Why? Because if you have a cation which is much large, like same +1 charge is there, much larger. Anion is much smaller. If I try to remove this particular anion, like you can imagine this total size of the cation is having just a +1 charge. So distribution of charge is not a, this distribution of charge is very poor, like very poorly the +1 charge is present. But here the charge density is greater. Because of that, if I try to remove a cation and anion, what happens is, although electrically neutral, the disturbance will be generated where you have greater charge density. That is why whenever you try to remove the cations and anions in equal number to form a Schottky effect, that will happen only when the crystal is ionic crystal and the ions should not differ much in size. Okay? Because if the ions differ in much in size, the charge density will be differed. If ions differ much in size, then charge density differs. Which disturb the crystal. And coordination number should be great. Like for these cases, you can have NaCl, CaCl, KCl, and AgBr as an example. Consequences of Schottky effect: the density of crystal decreases as ions were removed. The crystal begins to conduct electricity to small extent by ionic mechanism because of the presence of voids. Because of the, why the ionic mechanism is going to happen? Because of the presence of voids only. The presence of too many voids lowers lattice energy or stability of crystal. Obviously, if more number of ions have been removed, then obviously what is going to happen?
Will be unstable.
The presence of too many voids will lower the lattice energy or stability of the crystal. So Dimple says, sir, but when we will remove cation of bigger size, it will be removed. So how size will affect? Like imagine somewhere cation here is there. Cation is present at tetrahedral void, somewhere here it is there. And at the CCP you have anion. Cation is large in size, anion is very small in size. Anion is large in size, cation is small in size. Like charge density, if you try to measure, charge density, smaller size will have large charge density. When I try to remove the ion, like the charge density is going to be affected or not? Think of that. Like same +1 charge will have more density here, -1 charge will have less density there. If I try to remove equal number of cations and equal number of anions, but the charge density is going to be affected. Because of that, stability is going to be affected. That is why actually this defect we are not doing. Are we going and removing the cations and anions? No. The crystal itself has to show. We are just understanding the crystal. Yes or no? We are not removing the cation and anions. The crystal itself is showing the defect. What type of crystals are showing the defects means where cations and anions have same type of radii or almost same radii. Why means the charge density, it should not be differed greatly. If that is differed greatly, obviously the crystal stability will be disturbed. Okay, that was the reason. Frenkel defect. Frenkel defect means what? This is a type of point defect which is created when an ion leaves its appropriate site in the lattice and occupies an interstitial site. From the lattice, the ion is lost and it is not lost from the crystal, but occupying the interstitial site. So it is a vacancy defect at its original lattice point and an interstitial defect at the new position. Yes or no? It is both vacancy defect and interstitial defect combined. A hole or vacancy is thus produced in the respective lattice. The electroneutrality of crystal is maintained since the number of positive and negative ions is same. Since positive ions are small in size, they usually leave the position. Because the large size anions, they are generally forming the lattice, no? So positive ions which are present at void spaces, they leave the positions and they occupy the interstitial positions. And Frenkel defect is exhibited by ionic compounds where the radius ratio is differed in size or not differed in size.
Third
Radius
inside.
differed in size because the one of the cation has to occupy the interstitial sites. So if we have both cation and anion of equal size or almost equal size, then the interstitial sites cannot be occupied. So radius of cation by radius of anion should be low. Okay, examples are ZNS, AGBr, AGI, AGCl, radius of cation by radius of anion, that should be low. So these are the basic point. So the cation is going to show interstitial defect at the new position and a vacancy defect at its original position. So this is how the animation you can understand. The cation present somewhere that is now going to be occupied at the respective interstitial position. Because of that, what is going to happen? Because of that, you will have vacancy created here and positive charge will be present here. Now, what happens to the density? Can you say?
Increase.
Density, because ions are not completely lost, density of the crystal will be remaining same. Ions are not completely lost, so density of the crystal will be remaining same. What happened to the conductivity?
Increases.
Increases.
Like because of void, this is a void space, so ionic mechanism again, crystal becomes conductor. Okay, conductor due to ionic mechanism. Density is same, and here we can also talk of respect to dielectric constants. What happened to dielectric constants?
Increases.
Increases. Why? Because the like charges were now closely present, like dielectric constant increases. Earlier there won't be any great change in the dielectric constant because the ions have not moved close. Here the like type, the same type of ions, whenever they are closer, the dielectric constant will be increasing. Dielectric constant of crystal increases. And dielectric constant, higher dielectric constant means rapid dissociation if we talk in terms of electrolytes. With higher dielectric constant, the dissociation of the electrolyte into ions will be high. Right? Frenkel defects, consequences we can think of the same one. It is kind of a dislocation. Yes, obviously the crystal sites, it has to be, the particle has to be present at crystal lattice site, but it went to interstitial sites. So it is a dislocation defect. The closeness of like charges tend to increase the dielectric constant of the crystal. The crystal showing a Frenkel defect conducts electricity to small extent by ionic mechanism, and the density of the crystal will be remaining same. All these same points which you have discussed. Yes or no, students?
Sir.
Right. So this is how you can understand the stoichiometric defects, that is Frenkel defect as well as Schottky defect. Now we can think of impurity defects. Impurity defect means like as earlier we have discussed, NaCl is added to CaCl2 in the electrolytic reduction of NaCl. Like sodium, if you want to get in the metallurgy, we have added CaCl2. Same way, if molten NaCl containing a little impurity of SrCl2 is crystallized, some of the sites of Na plus ions are occupied by Sr plus 2. Each Sr plus 2 replaces two Na plus ions. It occupies the site of one ion and the other site remains vacant. So NaCl doped with impurity, addition of impurity is nothing but doping. NaCl doped with SrCl2 produces one vacant site for each Sr plus 2. So every Sr plus 2 ion will produce we have to remove two Na plus ions to place one Sr plus 2. So Sr plus 2 will occupy the position of only one Na plus, the remaining position will be vacant. Yes or no? So similarly, if you try to dope with Similarly, if NaCl is doped with GaCl3, it will produce how many vacant sites?
2 vacant sites.
Each Ga plus 3 will replace 3 Na plus to maintain electric neutrality. But out of these sites, out of these three sites, these three, only one is occupied. That is, 2 vacancies are produced. That is 2 vacant positions produced. You can see how the vacancy has been produced. SR plus 2 whenever it is obtaining, 2 Na plus have been removed and 1 vacancy has been produced. Non-stoichiometric defects. These type of defects are observed in the compounds of transition elements. These elements arise due to the presence of excess metal ions or excess non-metal ions. Non-stoichiometry means metal excess deficiency, metal excess defects or metal deficiency defects. Here what is going to happen? These type of defects are present due to excess metal ions or excess non-metal ions. So we'll study metal excess defects as well as metal deficiency defects in 2 perspectives. Non-stoichiometric defects are again 2 types: metal excess defects and metal deficiency defects. Metal excess defects are due to anionic vacancy. Metal excess defects due to anionic vacancy. So what happens is, whenever alkali metal halides are heated in the atmosphere of alkali metal, anionic vacancies are created. You can understand this. Listen to this point. I have a crystal, alkali metal halide like Na plus crystal, NaCl crystal I have taken. So we have Na plus ions, Na plus, somewhere we have Cl minus, somewhere we have Na plus, like this we have. This is a respect to alkali metal. Alkali metal halide crystal, we are heating this in the presence of sodium vapor. Sodium vapor, in the presence of sodium vapor it is heated. Whenever you try to heat sodium vapor, what happens? The electron, the outermost electron is going to be lost or not? Yes or no? Understand this point? Like this is NaCl crystal. This is with respect to NaCl crystal. We have Na plus ions and Cl minus ions at different crystal lattice positions. Above this crystal, we have sodium vapor. We are heating it. Because of heating sodium vapor, we have Na plus ions and electron. Na plus will be in the gaseous state. Those Na plus ions are now present, like the anion or halide ions, which are present inside the crystal. They have a tendency to form electrostatic attraction with the Na plus ions or not. Understand this point carefully. The Cl minus ions is in the crystal. Because of Cl minus in the crystal, it will come out, diffuse out, because Na solid is giving Na plus, Na sodium vapor is giving Na plus and electrons. The Na plus is present in the gaseous state. The Cl minus wants to develop new attraction with Na plus. So this is obtained from what? Na gaseous gives Na plus gaseous plus electron. The Cl minus at a specific lattice position that has been moving towards Na plus. Is that point clear or not? The Cl minus which was present at the lattice side that wants to develop new electrostatic force of attraction with Na plus ions, and in the crystal electrical neutrality has been disturbed or not?
Yes.
Because Cl minus we are removing means electrical neutral disturbed. So electron which was present or which was lost from the heating of Na, that will also diffuse back to this particular site. The electron lost by the metal atom will diffuse through the crystal, and those are present at these particular sites, and these centers with the electrons are nothing but F centers. What are they called as? F centers. Metal excess defect due to anionic vacancy. The anion has been vacated and that anionic position is now filled by electron. Why the anion is vacated? Because the anion want to develop new attraction with Na plus. So it went out of the crystal. Cl minus developed new electrostatic attraction with Na plus. At the original position, it has created the vacancy. That position of vacancy is occupied by the electron. So those electrons occupied at the specific anionic vacancies, they are called as F centers. And due to these F centers, the crystals will be colored. Are you getting these points or not?
Yes, sir.
Very interesting point. Metal excess defect. I have taken a sodium chloride metal, like any crystal. The above it we have sodium vapor. I am heating the vapor that is producing Na plus. So above the crystal we have Na plus. The Na plus ion which was present above the crystal, that will be attracted by the Cl minus. So Cl minus will diffuse out of the crystal. You may ask a question, sir, what makes the Cl minus move away? The thermal energy only. The thermal energy and the new electrostatic force of attraction. Because Cl minus is not free, it is also with the electrostatic force of attraction with other ions. So Cl minus will diffuse due to new electrostatic force of attraction and the thermal energy. We are heating it, no, the thermal energy. Because of that, the anionic vacancy is produced. That anionic vacancy is now occupied by the electron. So generating respect to F centers. Because of these electrons only, the crystals are going to show colors. When anionic metal halides are heated in an atmosphere of vapors of alkali metal, anionic vacancies are created. That is this same sodium we are heating in the presence of NaCl. The anionic or halide ions diffuse to the surface of the crystal from their appropriate lattice sites. Why? To combine with newly generated metal ions, Na plus. The electron lost by the metal atom diffuse to the crystal and they occupy here, and they are known as F centers, also known as Farben center or color center. Why it is known as Farben center or color center? Because these electrons are responsible for color. Is everything clear or not?
Yes,
Yes.
Yes, right. Metal excess defects due to anionic vacancy. The main consequence of metal excess defect is the development of color in the crystal. Different colored crystals we know. For example, when NaCl crystal is heated in an atmosphere of sodium vapor, it becomes yellow. Similarly, KCl crystal, when heated in an atmosphere of potassium vapor, it becomes violet. So the metal excess defects due to anionic vacancy is, that is nothing but your F center. So NaCl crystal, the new Na plus ions are coming. So Cl minus is lost, the electron gained, and NaCl is going to, the Cl minus lost will develop electrostatic attraction with Na plus to form NaCl solid, and the electron will occupy the respective anionic vacant sites, and those electrons are nothing but F centers, because of which only you have respective color. NaCl crystal is heated in an atmosphere of sodium vapor, it becomes yellow. Like salt also, you can see nowadays some different types of salt is there. Pink salt. Ever heard of this?
Yes, sir.
sir.
What is that? Why the color came? Because of such kind of defects only. Okay. There are some defects because pure NaCl is not having any color because there was no electron present. The electron is actually placed in this way. So like we can actually make the respective crystal lattice structure to show a different color. That color is due to the presence of these F centers. F centers are nothing but electrons placed at anionic vacancies. This is nothing but a respective electron positioned here, right? Sodium vapors, we are heating it. That is the NaCl crystal, we are heating it. What happened in the vapor of heated? So Cl minus are lost, and we are getting, you can just see the crystal lattice structure has been changed. This is a very good animation actually. This is NaCl, we are heating the sodium vapor. So what happens? Na plus ions are there. Cl minus wants to develop new attraction with Na plus to form a solid, and the vacancy positions are occupied by the extra electrons. So those are nothing but F centers. Metal excess defect due to interstitial cations. Now metal excess defect, metal should be excess. Metal should be excess due to anionic vacancies. Metal can be excess due to extra cations. Yes or no? If you want to be a topper, there are two options. You can be going into a section of students who are completely failures. Just based on marks we are talking. Okay. The real success is different. But just based on marks, if you try to think of, if you want to be a topper of a class, you can just find a room of students where all are getting very less marks. And in that class, you will be topper. The other option is you can study very hard, and with respect to any class also, you can be topper. Same thing, metal extra. Metal should be excess, means you can have less anions. So you can just remove the anions, thereby extra metal is there. That's the same thing we have seen in the absenta case. Metal excess due to interstitial cations. The metal ions can also be positioned at the interstitial spaces where you have extra metal. So metal excess defect due to interstitial cations. This type of defect is shown by crystals which are likely to exhibit Frenkel defect. Why? Because the interstitial positions has to be occupied by the cations. No, interstitial positions has to be occupied by cations means similar to Frenkel defect only we have the scenario. Yes or no? The interstitial positions have to be occupied means you can be having a small cation occupying the interstitial sites. An excess positive charge is located in the interstitial sites. To maintain electrical neutrality, an electron is present in the interstitial sites. So an example showing this type of defect is ZNO. You try to look at the ZNO crystal structure. When you try to hit zinc oxide, it forms Zn plus 2 and oxygen is going to be lost and 2 electrons are lost. The excess Zn plus 2 ions are accommodated in the interstitial sites and the electrons are enclosed in the neighboring interstitial sites. The yellow color of the yellow color of ZNO, when hot, it is due to these trapped electrons. These electrons also explain electrical conductivity in ZNO crystal. You take a zinc oxide crystal, we have Zn plus 2, O2 minus ions. Because of heating ZNO, O2 minus ions have been lost in the form of oxygen. So some of the vacant positions are there. But the Zn plus 2 which are excess, they will occupy the interstitial sites. And the electrons which are present, they will also be present at the subsequent other interstitial sites to maintain electric neutrality. To maintain electrical neutrality. So this is a scenario, metal excess due to interstitial cations. So we have that interstitial cation. We have the electron present here, so that electrical neutrality has to be maintained. Metal excess defects due to interstitial cations is going to be happen, so that the electron should also be present at the subsequent near interstitial sites, so that the total crystal has to be electrically neutral. If not, the crystal is not stable. If the total crystal is not neutral, how can the crystal would be stable? It will be easily affected by other type, like if the total crystal has some positive charge, it will be affected by negatively charged species. So stability of the crystal has been lost, right? And then we have, yes, very good. And then we have the last type, metal excess and metal deficiency will also have. There are many solids which are difficult to prepare in the stoichiometric composition and contain less amount of metal. These are metal deficiency defects. Metal deficiency defect. A typical example of this type is iron oxide, which is mostly found in the composition of Fe 0.950. Fe 0.950. This is a respect to iron oxide. It may actually vary from Fe 0.9302 to Fe 0.960. Stoichiometry is not present. In crystals of FeO, some Fe plus 2 cations are missing, and the loss of positive charge is made up by the presence of required number of Fe plus 3. Understand this last point carefully. We have FeO crystals, Fe plus 2, O minus 2, Fe plus 2, O minus 2. Like that, we have the ions placed. In crystals of FeO, some Fe plus 2 are lost. because metal deficiency, no, some metal ions are lost. If one Fe plus 2 is lost, how much charge is lost? Plus 2 charge is lost. So the subsequent other can be Fe plus 3. The subsequent here also Fe plus 3 can be present. So charge is going to be neutral or not? Some of the metal ions are lost, but to neutralize charge, electrons are not coming, or the just the same metal ions from the plus 2 state went to plus 3 state in case of iron. So if some of the Fe plus 3 ions are present, obviously charge neutrality is maintained. So in crystals of FeO, some Fe plus 2 cations are missing. For one cation missing, we have 2 Fe plus 2 has to be oxidized to Fe plus 3. And the loss of positive charge is made by the presence of required number of Fe plus 3 ions. Is that clear?
Yes, sir.
Yes. We can have this ideal crystal where you have this scenario Fe plus 2 O2 minus Fe plus 2 O2 minus. Now what is going to happen is, from the ideal crystal, this is Fe plus 3, like one of the iron is Fe plus 3 and the other is Fe plus 3 and one of the Fe plus 2 is lost. You can see now. So to maintain like metal is deficient now, metal deficiency defect, but the electrical neutrality has to maintain. So the sum of the metal ions has been oxidized so that neutrality can be maintained. Is everything clear, students, so far?
Yes, sir.
So these are the different kinds of defects which you can study. And the last point which you can think of is with respect to the solid state is properties of solids. How many like two types of properties are there? Properties of solids. What are the two properties which you can think of? The first one is electrical properties and the other is magnetic properties. Electrical properties based on conductivity, what you can say? Based on the values of conductivity, solids are classified into
3 types.
what are those?
Conductor, insulator, and semi.
Very good. Based on the values of conductivity, solids are into 3 types. Solids are classified into 3 types. What are those? Conductor, insulator, and semiconductor. Insulators, what happens, students? Conductivity is very high for conductors, very low for insulator, and for semiconductor it lies between the conductors and insulators. Very high conductivity for conductors, very low for insulators. Insulators are not going to be conduct electricity, and semiconductors, the conductivity will be between conductors and insulators. Why in conductors the conductivity will be very high?
Due
Like-
to free.
Like in a conductor we have valence band and conduction band, yes or no? Like in insulator also we have, in semiconductor also we have. In conductor, what happened to the valence band and conduction band?
Energy gap. very low.
Gap is
Like can I say they'll almost be very close? In conductor, valence band and conduction band overlaps.
yes.
Yes.
Sir.
What is valence band?
Valence electrons.
So we are saying that valence band and conduction band overlaps in conductor, but what is valence band first of all?
Outermost electrons. Of the
Valence bond or valence band?
Sir, I mean in a whole solid, all the outermost electron forms a valence band.
Okay. So what is valence band means? It is nothing but the molecular orbitals. In solids, the atomic orbitals of different atoms are there. Different atoms will have, like every atom will be having the respective atomic orbitals in different shells. The atomic orbitals of atoms combine with each other to form molecular orbitals. And these molecular orbitals will lie very close in energy and thus they form band. Okay. Understand this point? If you talk about a solid, we have a lot of atoms. In an atom itself, we have atomic orbitals. The atomic orbitals of all the atoms, they are lying very The atomic orbitals of one atom can combine with other atom to form molecular orbital. The molecular orbitals thus formed, they lie very close, very close, very close. Thus, they will lead to the formation of band. Valence band. In the valence band, we have the valence electrons. These are nothing but very closely packed molecular orbitals. Valence band is nothing but very closely packed molecular orbitals. So whenever we have insulator, valence band and conduction band, very large difference is there. Insulator means valence band and conduction band. The electron can't move easily from valence band to conduction band. In a semiconductor, what is going to happen in a semiconductor? In a semiconductor, low energy difference between valence band and conduction band. Conduction band and valence band will be close. Difference between conduction band and valence band is high. Energy difference between valence band and conduction band is low, right? Valence band is nothing but atomic orbitals of different atoms combine with each other to form molecular orbitals, and these molecular orbitals which are closely packed are called, or forming a band, will form a band called as valence band. Will form valence band. From that only we explain the concepts of Fermi energy levels, okay, trap sites and all. In conductors, what happens if you try to increase temperature? Conductors, increase temperature. If I try to increase temperature, the electron can be easily going into the respective conduction band easily. Can I say conductivity is increasing in that way because electronic motion is increased?
Yes, sir.
Yes or no? With increase in temperature in conductance, what happened to the conductivity?
Conductivity increases.
Increase.
Are you sure? In
So when we-
conductors are actually classified into two types: electrolytic conductors, metallic conductors. Okay, conductors are actually two types. What are those types? Electrolytic and metallic. With increase in temperature, conductivity increases in electrolytic, whereas conductivity decreases in metallic. With increase in temperature, conductivity decreases for metallic conductors because the molecular motions increase. That is, the crystal lattice sites, wherever in the crystal lattice sites, whatever the atoms we have, those vibrational frequencies will be very high. Like if you consider any metallic conductor, here you have a particular metallic crystal, like lattice point, the vibrations are going to be high, so the electron can't flow easily. The obstruction of electron is high. In conductors, which are classified into electrolytic and metallic, with increase in temperature, conductivity increases for electrolytic conductors. With increase in temperature, conductivity decreases for metallic conductors. Semiconductors, for insulators, we will not be talking about conductivity because it is very, very low. For semiconductors, what is going to happen with increase in temperature?
Increase.
Increases.
With increase in temperature, conductivity increases. Okay, semiconductors are now under a lot of usage, right? If temperature is increased, why the conductivity increase in semiconductors? Because semiconductors are generally formed by which group elements?
14th.
Group 14 elements generally form. Group 14 elements generally form semiconductors. If I try to increase, what happens, students? The bonds will break or not? Because of bond breaking, the number of free electrons increase. Because of increase in the free electrons, conductivity increases. Group 14 elements generally form semiconductors like silicon, germanium. So now what is going to happen is we have a system like this: silicon, 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 silicon. So every atom is going to be connected with 4 other atoms. In that case, what you can see, if I try to increase temperature, this bond is going to be cleaved, free electrons increases. Because of increase in the free electrons, conductivity will be increased. But the semiconductor device which I want to use, that I have to operate at normal temperature. It is not like I have to increase the temperature very high so that the conductivity increases so that the device can be used. That is not the scenario. We have to use the same device at low temperature. So I have to increase the conductivity of semiconductor so that it can be used in different devices, but not by increasing temperature. So the conductivity of semiconductor can also be increased by,
Heading impurities.
okay, very good. The conductivity of semiconductor can be increased by doping as well. That is adding impurities. What type of impurities you can add? You can add a group 15 impurities as a group as well as group 14. Group 15 impurity will add first. If you try to add group 15 impurity, you have silicon here, you have silicon here, you have silicon, group 15, any group 15 element you say?
Nitrogen.
Nitrogen. The first element you can remove because of exceptional properties. Nitrogen, phosphorus, arsenic.
Arsenic.
So now in the group 15, how many valence electrons should be there?
5.
5 valence electrons, but group 14, only 4 valence electrons. So one extra electron is there, right? Group
Yes,
15
sir.
impurity, whenever I add, because of the presence of extra electron, what is going to happen? If I place positively charged plate here and negatively charged plate here, the electrons will move towards
Positive charge.
positively charged plate. So you can say the increase in conductivity can be happened, and that is why what type of semiconductors they are? P type or N type?
N-type.
N type semiconductors. We can also add group 13 impurity. Group 13 impurity you add.
Boron.
Like we
Germanium.
have silicon,
Gallium.
like we'll add gallium. If you try to add gallium, what is going to happen? It cannot form 4 bonds because only 3 valence electrons are there. Like the other silicon atom will have an electron, but here we have some absence of electron. That absence of electron you can imagine as a hole.
Hole.
Now if you try to apply the same electric field, what is going to happen? The positively charged plate present here, negatively charged plate present here. Now what happens is, to occupy this hole, that is electron vacancy, that is nothing but your hole. To occupy that hole, the electron present on the subsequent silicon atom, that will move. So electron will be occupying this position and new hole is generated here. Yes or no? Can I say like this? Electrons are present here now, new hole is generated here. So can I say holes are moving towards, holes are nothing but electrons will be moving towards positively charged center and holes will be moving towards holes. Like this is your respect to negative charge, let us say, and electrons are there in this fashion. So electron present here will move to this position and generates a hole. So electrons are moving towards positively charged plate. That also can be understood as holes moving towards the negatively charged plates. So what type of semiconductor it is? P-type semiconductor. Hole is nothing but a vacancy of electron, students. Hole is not a particle, it is a vacancy. It is a vacant position where electron was not there. This was how you can actually increase the respective conductivity of group, like a semiconductor's conductivity can be increased by doping. So like doping, you can, group 15 impurity means N-type semiconductor, group 13 means P-type semiconductor. So these are the electric properties. Then you can also consider magnetic properties. Magnetic properties, the electrons present in the respective atoms, they will have spin motion as well as orbital motion. Spin and orbital motion of electron, we can write due to spin and orbital motion of electron, the electron itself behaves as a tiny magnet. The electron itself behaves as tiny magnet. So if you have a paramagnetic substance, paramagnetic means Paramagnetic means weakly attracted or weakly repelled?
Weakly attracted.
Weakly attracted by external magnetic field. External magnetic field. The paramagnetic substances are weakly attracted by external magnetic field, which is due to presence of unpaired electron or absence of unpaired electron.
Presence of unpaired.
Presence of unpaired electron. Unpaired electron. What is diamagnetic?
Weakly repelled.
Weakly repelled by B external. What is B?
Magnetic field.
Yes, magnetic field due to absence of unpaired electron. Ferromagnetic,
Strongly attracted.
Strongly.
paramagnetic and diamagnetic, you can easily compare. Like just to try to compare the whether unpaired electron is present or not. Ferromagnetic and ferrimagnetic, what you can say? What is ferromagnetic substance? Ferromagnetic, ferrimagnetic, anti-ferromagnetic. Yes or no? Ferromagnetic means what?
Strongly attracted.
Ferromagnetic means strongly attracted by external magnetic field. Strongly attracted by B external. But this is not the scenario to understand completely. The magnetic moment, whenever you try to, if you try to apply the external magnetic field, all the magnetic domains are going to be present randomly. So in case of ferromagnetic substance like metals, since very high number of electrons are present, magnetic domain has to be taken. What is magnetic domain?
Magnetic dipoles.
Okay, magnetic domain, can I say magnetic domain is the magnetic moment of a small part of crystal. Is the magnetic moment of a small part of crystal. If the magnetic domains in the absence, okay, absence of B external, the magnetic domains, how they are arranged? They'll arrange in different directions. Okay. In the absence of external magnetic field, the magnetic domains arrange in different directions. But in the presence of external magnetic field, all the magnetic domains will arrange in the same direction. In that case, we can say it is a ferromagnetic substance. Ferromagnetic substance is what? All the magnetic domains will arrange in the same direction in the presence of external magnetic field. Antiferromagnetic means
Oppositely arranged.
equal number or unequal number?
Equal number.
Antiferromagnetic substances and ferrimagnetic substances. In the antiferromagnetic substances, one above means other is going to below. Like we can have examples, magnetic domains arranged in this fashion. Equal number of domains in opposite direction. Okay. Equal domains, equal magnetic domains in opposite direction. This is the fourth one. Third one, this is example GD. Gadolinium is an example of ferromagnetic substance. Ferrimagnetic means unequal number will be there. Unequal number will be there in the
Randomly arranged.
unequal magnetic domains in opposite directions. Antiferromagnetic, you can take an example of MnO. Ferrimagnetic, you can take an example of respect to ZnFeO4. Okay. Different examples you have to remember as far as all the magnetic species have been given. So as I was saying, you just remember all the examples whatever you are given in NCERT. Along with that, Allen module, whatever the examples have been given under different category, you have to be perfect with that examples. And we also have piezoelectric substances. What are piezoelectric substances?
Quartz.
Yes, piezoelectric means with the help of mechanical stress, if we can produce electrical energy, then that is said to be piezoelectric in nature. So these are all the different concepts as far as solid state can be considered. Fine, students. Thank you all, everyone. Bye.
Thank you, sir.
Thank you, sir.